So, so far we have discussed about signals, little bit of system, and then try to describe about the modulation scheme which are employed for amplitude modulation mostly. And then we started characterizing different kind of amplitude modulation that are there. We have done a comparison and finally we discussed about little bit about the channel. Okay. And then we said that one of the most detrimental part of channel, which will be probably either channel or receiver, or I should say rather impairment, is noise. This is something we have already said. But to understand noise, probably we have to really understand random process. So, what we will try to do, probably give you a brief overview of random process, but I do not assume any prerequisite. So, what I will do, I will give a first a brief overview of probability theory, basic probability theory, and then from there we will go to random variable, and then from there we will develop the theory of random process probably, which will be all targeted towards communication or characterization of noise. So, let us start with the concept of probability. So, we all know there are events which are means eventually looks to be random to us. Okay. So, let us just discuss one event which is almost known by everybody, like either tossing a coin or rolling a die, right. So, whenever we do that, we say that it is random, but most probably it is not random, as we state that. Means whenever we toss a coin, if we can calculate all the forces that is being exerted on that coin, let us say which angle I put it on my nail, and then when I toss how much force I give in which direction, and the air friction and all other things, if I just gravitational force, how it changes with time. So, everything if I calculate and then probably elasticity of the ground where it is hitting. So, if I can calculate all these things, probably there will be no randomness associated with it. I can definitely calculate and tell you what will be the outcome of this event. Okay. But as I have started describing, you might have seen that there are lot of process, complicated process involved and associated physics involved in it. So, if I really wish to take a journey into that and try to calculate this, this will be a tedious job, which as in any engineering or scientific study, we do not want to do that. We really wish to get some extract or some meaningful information from there and then try to see whether that can be used further. So, this is something where probability theory came into picture. What people started doing, they started looking into that particular random event I have talked about, that tossing a coin. Instead of going through the entire physics of means tossing the coin, means exerting the force and then coin flipping in the air and dropping in the ground. So, instead of going through all this physics, they started thinking that okay, given all those things, let us try to see what is the outcome of that, okay, that experiment. So, if it is a coin and we assume that the coin whenever it is landing, it is not landing on its side or edges. So, it will be probably landing on either of its face. So, there are only two outcome of this entire process. So, one is we call it head or tail. Okay. So, these are the only two outcome of this whole experiment, right. Then people started saying, okay, if this is the only two outcome, why do I have to go through all these details? Let us try to see intuitively can we give some understanding of this events. Okay. So, because finally I need to see whatever happens, what is the overall outcome and what is the associated means mathematical understanding of or physical understanding that we can derive from this process instead of going through all these details. So, people started saying, okay, if this is the case, let us try to do it this way, that I will take either that single coin and I will keep flipping it. Okay. So, I will do this, I will keep repeating this experiment. Okay. Let us say n number of times, and after every time I do this experiment, I tend to record what is the outcome. okay, and I start counting it. So, out of this n, how many times, let us say n1 times, I have observed that head has occurred, and definitely n minus n1 times, because we have already assumed there is no other outcome. So, it will not land on age of the coin and all those things. So, n minus n times there will be tail. Okay. And then people started questioning that what is the relative occurrence of these things. Okay. So, or let us say frequency of each of those events which will be happening. So, the frequency is, if I just take this experiment, this simple experiment. So, I say from that experimental outcome, I can say n1 by n, that is the relative occurrence of, I say, head. So, let us call that as ph, okay, and pt is some n minus n1 divided by n. Okay. And if I now start doing this experiment for a very large number of time. Okay. So, what does that means mathematically? That I will take limit n tends to infinity, okay. And people started doing that, and then they could observe that if the coin is, means we should say unbiased coin, or the coin we see that it has no preference for any one of the surface, head or tail, whenever it is landing. See, it might happen sometimes that the edge is designed in such a way that it has a preference towards a particular surface. It might happen that it is little tilted over there. So, if that is not the case, people have seen that this n1 almost tends to become n by 2. Okay. And finally, what we get? So, we get this PA, which is limit n tends to infinity, n1 by n, that goes towards half, and same thing happens for, sorry, pH, and same thing happens for pt, that also goes to half. Okay. So, this was probably the initial definition of probability. Okay. So, people started saying that probability of this particular event head happening is half. That means, if I just do this experiment for n number of times, I will almost see n by 2 times head is occurring and n by 2 times tail will be occurring. So, this is the frequency definition of probability. So, I associate with every event that are the outcome of that experiment, whatever random experiment I am doing. So, those events I associate with a value which is called probability. So, this is just percentage, I should say, means or I should not say percentage, it is just a fraction that defines how much, means if I just multiply that with 100, probably that will give me how much percentage of time it will favor a particular outcome. Okay. So, that is actually the definition, very definition of probability. This is called the frequency definition of probability, and all this number, this half, that is a magic number which has come from basically experimentation, pure experimentation, like any other scientific experimentation. Okay. So, these are the axioms, we should say axioms of probability, and these are just basically observed over time, and people have understood that probably this should be the case. Okay. There is no basis that this should be happening. People have not solved the behind, means underlying physics to try to come up with this. They have seen, they have tried testing with different number of coins in different location, with different number of times, with different kind of people who were tossing it. So, they have seen all these observation, and everywhere they could see that it is close to this, and that has given that axiom that okay, that should be the probability. From there, something else comes into picture. Okay. So, people started defining, instead of this definition, they started defining that whenever I do a experimentation, how many equally likely events are possible in a particular experimentation. Like in this experiment, I have head and tail which are equally likely. Okay. So, whenever I start calculating the overall probability, so I count those equally likely or equal possible events. Okay, I count those things and then create a space. Okay, so, like here I have a space of head and tail, only 2 elements are there. Okay. And we say the probability of head will be, out of them, for that particular event we are calling, means this will be more clearer with a bigger example probably. Right now we are just defining it. So, for the event we are targeting, how many equally likely elements are favorable to that event. Okay. Here for head there is only one event which is favorable, tail is not favorable towards head, because if it is tail then it is not head, right. So, only one event are favorable towards this, divide by as many events are there, equally likely events. So, 2, I get the same answer, right. Same thing happens for PT, that should be 1 by 2, right. There are 2 events, out of them favorable to head is 1. Okay. So, let us just give one little bit bigger example and then probably you will understand little bit more. So, let us try to say, suppose I have a 6 face die, okay, and I roll it, and we say that the die is fair, that means any surface appearing at the top is equally likely. Okay. So, that means how many events, equally likely events are there, already by my definition I get 6 equally likely events, right. So, I can define them as A1, A2, A3, A4, A5 and A6. That means in the top surface 1 comes, top surface 2 comes, top surface 3 comes and so on. Okay. So, there are 6 such events and that define my entire space. Whenever I define this collection of events, I call this a sample space. Okay. That is a definition. By definition I call this a sample space, and these are the individual element of that sample space. So, these are the elements. Okay. It is just the abstraction we are trying to do. Okay. All of them we have already told by definition are equally likely. Okay. Now, let us say that I define an event, now we are just diverting from this. I could have defined an event which is that I will be, means what is the probability that I will be receiving 1 in the top surface. So, that is actually there are how many are favorable to this particular thing, it is only 1, this one only will give me 1, all others will be giving me something else. So, 1 divided by how many total events are there, 6. So, it should be 1 by 6. Similarly, if I talk about 2, that should be also 1 by 6 and so on. But if I just now change the definition or change the definition of event, let us say my event is that whenever I roll a die, what is the probability that I will be getting a even number. Okay, that is the event definition now. So, out of them now you can see the favorable elements. So, 1 can appear, 2 can appear, 3 can appear, 4 can appear, 5 can appear, 6 can appear. Out of them this will give me a even number, this will give me a even number and this will give me a even number. So, how many are favorable to my experimentation or my definition of event, that is 3 divided by total number of elements, that is 6. So, that probability of getting even number is half. Similarly, probability of getting odd number is also half, right. So, that is how we define event over here. Okay. So, let us say suppose the same thing we take it. So, let us say this is A1, A2, A3, A4, A5 and A6, that is my sample space. I call it S. Okay. So, the sample space, now I will give a set theoretic definition of this particular thing. So, sample space actually is a group of elements. So, I can call that as a set. So, this particular set is defined by these elements A1, A2, A6, 6 elements are there. Okay. Out of that I define an event which is called A, or I should say AO. That means the event that has element which are actually showing me odd number in the top of the surface. Okay. So, AO, which is this. So, I can write AO as within the set, it is just a subset which has the element A1, A3 and A5, right. Similarly, I can write AE, that is the even number which happens to be this, A2, A4, A6, right. Up to this it is all fine, right. Now, I start defining something else, because now I will actually go inside the probability theory. Okay. So, let us try to define another event which is telling me that whenever I roll a die, my event is that I should observe a number which is less than equal to 4. Okay. So, who should be the part of this particular event? That should be these things. So, either 1, 2, 3 or 4, those are all less than or equal to 4. So, I call that event B, fine. So, I have defined now 3 events within the same sample space. Okay. I have 6 elements, and with that I started defining events. So, I have a definition of events, and accordingly I have defined some 3 events. So, this is A1, A2, A3, A4. Now, in terms of set theory, let us start calling the union of event and intersection of events, okay. Because I have 2 events. Now, let us try to see if I can define. In set theory we know about union, that means taking the elements of elements either that exist over here or there, that is union, and intersection is it should be and, that means it should be both existent on both the set or both the I should say collection or subset. So, if I just try to write A0 intersection B, what do I get, or AO intersection B. So, this is my AO, this is my AE. So, this has element this and this, A1 and A3, right. Similarly, I can define AE intersection B, and this has element A2 and A4. Okay. So far I have still not gone into probability. Okay. I am just trying to see the events and their intersection or union. If I try to write the union of this, intersection of this, what do I get? That is a null set, because these two has no common event. So, I can write that as a null set, or I can write it this way, no events are included in that, okay, or no elements are included in that. And of course, AO union AE must be giving me S, the overall set. Okay. So, these are some of the things we have observed. Now, let us try to see if I wish to from that definition, if I wish to calculate the probability that AO intersection B is happening, okay, or probability that AO union B is happening. So, this I should say joint event simultaneously AO and B happening. Okay. So, that means I would say that I roll a dice, what is the probability that the number I will be seeing that is both even and less than 4, that is this event and the associated probability. And if I say that what is the probability that both are, means the event that are happening, those are both odd as well as less than 4. So, that should be this and the associated probability value that I wish to assign. Okay. Probability means again that same definition, that if I have all outcomes, now it is becoming a little bit more complicated. Earlier it was much more simpler, now it is becoming more complicated because I have joint event defined. So, both the things should be satisfied. What is the relative frequency of that? How many times if I start doing this experiment, means that means n number of times I roll the die, and if n tends to infinity, what should be the number of times that I will be seeing this particular joint event occurring. Okay. So, that is what we wish to evaluate. Okay. So, if I wish to evaluate that, how do I evaluate this particular things? Okay. So, first of all, let us try to see if I wish to do it for this one. Let us say probability of this. Okay. Probability of AO union AE. Okay, this is something I wish to do. Now, AO and AE has no common element, right. What I can do, I can basically individually calculate, the probability axiom says that I can individually calculate the events and their associated probability and I can add them. It is very simple, it can be easily observable, because if I just do the experiment for n number of times, whichever number of times this will be happening, this will not be happening. Okay. So, if I observe them as n1 number of times and if I observe this one as n2 number of times, they should be completely, if this is happening, this will never be happening. That is not the case. I cannot say that same thing for A, AO and B. I cannot say these things. Okay. So, whenever I will be calculating, suppose AO union B, I will not be able to say this thing, that a particular event that is favorable towards AO, that is not favorable towards B, or it is probably the proper term is mutually exclusive. That means, if AO happens, B will not be happening, I cannot say that. There are elements where both the things will be happening, right, and there are elements also where one will be happening, the other one will not be happening. So, this kind of complicated definitions are already observed over here, but in this case, whenever I have this definition, that means they are, we call this as two sets are mutually exclusive, they do not have any common elements. If that is the case, then whenever this will be happening, suppose I keep counting, this n1 is the count that AO has happened. Whenever AO has happened, I am sure that the other one has not happened, and whenever the other one has happened, I am sure that this one has not happened. So, therefore, if I just count this one and this one, overall this union has happened can be just summation of them, I am sure. Okay. There will be no extra term counted if I just add these two, wherever in this case there are some commonality. That means, there might be one experimentation where I get, suppose AO and B I am talking about. So, I get, suppose it is odd number, so I get 1, that is one valid experiment. So, that particular one I count for which one? Should I count it for this one or this one? Basically, it will be counted for both of them, but this is just one experiment. I am counting 2 times. If I just add those counting, it will just take extra count, and obviously the means derived probability value will be wrong of this joint event. So, that is the problem over here. If they are mutually exclusive, I can do this, and then I can write limit n tends to infinity, that is the probability of this event AO union AE, and then I can separate them, limit n tends to infinity n1 by n plus limit n tends to infinity n2 by n. This is exactly the probability of AO. So, I can write this as probability of AO plus this is probability of AE. So, this is actually where probability gets distributed over the union if the events are mutually exclusive. Okay. So, that is probably the first axiom of probability theory that we can get. If we can define two events which are mutually exclusive, then the probability gets added. Okay. If they are not mutually exclusive, then what happens? So, basically what we can see, just see it from set theoretic point of view. So, I have a set A, I have a set B, right. I wish to do A union B. So, what will happen? If I just take as many times A happens plus as many times B happens, then this particular section will be counted twice. So, I have to take that out. So, therefore, this must be P of A0 plus P of B minus P of A0 intersection B, I can write this. So, that is probably the, as long as they are not mutually exclusive, that is probably the second axiom of probability theory, that if two events are not mutually exclusive, I have to do it always this way, okay. This particular case, right. So, now let us try to see that union, if I wish to calculate, if I know individual event occurrence, those are good, but I also have that intersection. So, I have to now try to evaluate the intersection of a occurrence. So, let us say this, I wish to calculate this, right. So, this is something I want to calculate, okay. So, how do I do that? This actually means that both the things has happened, right. So, let us say things event A0 has also occurred and event B also has occurred. Let us try to again do the frequency definition. Let us say I have rolled the die for n number of times, okay. Out of them I have seen that n1 number of times B is occurring, okay. So, basically I am just trying to see that n times I have rolled the dice, I am just counting where B has occurred, I am not bothered about AO now, okay. So, I am trying to see where B has occurred, because I wish to evaluate where AB are both occurring. So, if AB are both occurring, B has to occur. So, I am just counting those numbers where B has occurred, that is n1, okay. Out of them, how many times A has occurred? Now, there is a restriction, given B has occurred, because this n1 times I am filtering out, those are the event, means those are the outcomes, or those are the experimental outcome where I have seen B, event B has occurred, okay. That means I have seen some, suppose B is that less than 4, so that has occurred, okay. Out of them I am now trying to evaluate how many times A has occurred, let us say that is n2. So, n2 is actually a number where it is basically, this is counted from that set of n1, those events only I have observed. Out of them, wherever A also has been satisfied, I am just counting out them. So, it should be, I always know that n2 must be less than equal to n1, that should be the case, because out of them only I am trying to see, okay. So, this is where A has occurred given B also has occurred, okay. So, that is the definition, or that is how it is being written, that event A, or I should say event AO has occurred given that B has also occurred, okay. So, I can just now get this A intersection B, what is the definition of that? Limit n tends to infinity, finally A intersection B where both A and B has occurred, that is actually n2. So, it should be n2 divided by capital N. This n2 I can write, so this I can write as n2 divided by n1, n2, n1 divided by n, that is simple, just both sides I have multiplied and divided by n1. Now, let us divide the limit n tends to infinity, n2 divided by n1 and limit n tends to infinity, n1 divided by n. Now, what is this and what is this? This is very clear. This was the first experiment, right, where out of that n number, n1 number of time B has occurred. So, that must be the probability of B, right. What is this? This is actually probability that given B has occurred, what is the frequency of A occurring. So, this must be the probability that AO has occurred given B has occurred, this particular part, because it is n2 by n1. So, that n1 number is already telling that B has occurred. Out of them, or Out of those experiments where B has already occurred, I am trying to see A has occurred. So, this must be the probability that AO has occurred given B has already occurred, because whenever I am trying to calculate this, that means I have already ensured that B has occurred. Okay. So, that is where the conditional probability comes into picture. This is called the conditional probability. This actually means that a particular event, condition on that a particular event has already occurred, what is the associated probability that another particular event will be occurring. Okay. So, we could now evaluate by this definition, frequency definition, that what is the intersection probability. What we will do in the next class, we will try to see the implication of these things. Okay. So, we will discuss these things in details in the next class. Thank you.